Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today our lesson deals with chemical reactions, and some of the concepts that are covered include recognizing chemical changes, representing chemical changes, law of conservation of mass, and guidelines for balancing chemical equations. I've written a paragraph or two here about reactions. I hope I can read it well for you. You know what a bad reader I am. Every second, living organisms in society, hundreds of chemical reactions are taking place. Respiration and photosynthesis are two natural processes that are most important to us, and they entail many reactions such as in the Krebs and Calvin-Benson cycles. The process of cellular respiration, which includes a series of reactions, is responsible for providing us with the energy that sustains our life. During this process, glucose is combined with oxygen to produce water, carbon dioxide, and energy. During the process of photosynthesis, molecules of carbon dioxide and water combine in a series of reactions to make glucose and oxygen. Plants use glucose molecules as the building blocks for the manufacture of other compounds such as starch, protein, fats, and vitamins. The energy for the latter process is provided by sunlight. Other organisms called consumers survive on the food manufactured by plants. Without these two processes, life would come to a standstill. However, the vast majority of other reactions are man-made. Human activities run the gamut from the combustion of various types of fossil fuels to the synthesis of myriad of compounds such as chemical fertilizers, pharmaceuticals, fabrics, paints, and plastics. While these activities and their products are beneficial to us in many ways, they are also having profound effects on our environment and the quality of our lives. For example, the combustion of fossil fuels that powers automobiles, aircrafts, and factories produces gaseous oxides such as carbon dioxide, nitrogen dioxide, and sulfur dioxide that combine with water to form acidic rain. Acid rain can destroy vegetation, aquatic organisms, soils, metals, and marble infrastructures. Carbon dioxide is one of the gases mainly responsible for global warming. The incidence of lung cancer, emphysema, silicosis, pulmonary fibrosis, and some types of cardiovascular diseases is much more prevalent in highly industrialized areas than in non-industrialized areas. What step should be taken to mitigate the effects of these changes in our life? And these are some questions for all of us to answer. So now we're going to go to how we recognize chemical changes. In chemical changes, the original substance is changed to one or more new substances that have different physical and chemical properties than the original one or ones. Look at this reaction, for example, and we try to see whatever the products are and compare them with the reactions. Here you have magnesium. I don't know how many have seen magnesium being burnt. A very bright flame is created when this thing is burnt. You have magnesium being burnt in oxygen here, and it gives you magnesium oxide and energy. So this is a shiny metal. This is oxygen from the air, and this is a white solid. So right away now you can see the change in physical properties. This is a metal here, is a solid. This is also solid here, but this is shiny and that is white. There's a colorless gas here. So the change in state for this one, and there is find that there's a metal here, and this is like a solid, powdery solid here. Physical chemical changes. The magnesium oxide that is formed here can react with water to produce a basic solution of magnesium hydroxide. These guys here do not react with water to produce anything. This can only react with steam. So these are some of the chemical and physical changes that took place in that reaction there. What are some of the evidence for chemical reaction? How can you recognize chemical reaction? One, formation of a solid, what's called a precipitate. If I have a colorless solution here of sodium hydroxide, and I have a blue solution here of copper 2 sulfate, and then pour either one into the other one, you will get a blue gelatinous precipitate here that sinks to the bottom, and here you're going to see a clear solution, if you allow that to stand for some time, of sodium sulfate. So this is the evidence here. You get a solid being formed here. In this case, it's copper 2 hydroxide. This is a blue gelatinous precipitate. That's one of the evidence you'll look for. Number 2, evolution of a gas. If I have sodium carbonate solution and I react that with hydrochloric acid, what you will get is a solution of sodium chloride and water, and you see evolution of a gas. You see effervescence or fizzing taking place, and the gas that comes out there is carbon dioxide. You sometimes encounter the same thing in your stomach. You know, sometimes you drink pop soda and you burp. What you're burping there is carbon dioxide, because the acid inside the stomach there is reacting with the weak solution of a carbonate that's found in the soda, and you get this reaction taking place. So the gas that you're burping up there is mostly carbon dioxide. Anytime a gas is produced, that is sign of a chemical reaction. Number 3, energy changes. Here you're having burning of methane gas in the oxygen, and you get heat and light. Or in your lab, you burn this propane gas here, you put your hand there, you feel hot, and that's a blue flame being produced there. So energy changes in the form of heat, light, and also sound. Lots of sound taking place in some parts of the world right now. Color changes. If you react lead-2 nitrate with a solution of potassium iodide, you'll get a yellow precipitate of lead-2 iodide. And of course, you can see lots of color changes that are taking place in nature, and all those are indicating to us that chemical changes are taking place. For example, during the fall, you see these leaves, they undergo all different color changes. If you leave your bike outdoor for a considerable period of time, you will notice that brown solids appeared on its rims. That is due to the reaction of the iron present with the water and oxygen to form rust that is brown. Odor formation. If I burn sulfur in oxygen, you get sulfur dioxide. If you burn a match, for example, you can smell sulfur dioxide. Okay? If you want to go further, when you burn a match and you want to check the nature of the gas, you can see the acidic nature of the gas. If you take a piece of damp blue litmus paper and you put it over the burning match, you find that the damp blue litmus paper will turn pink, which is indicating to us that an acidic solution is formed on the litmus paper. That's because when sulfur dioxide reacts with water, it forms a weak solution of sulfurous acid. Here are some chemical equations here, and you're asked to study them and identify the evidence for any chemical change that takes place. And of course, the answers to these are found in the solution manual. Representing chemical changes. There are two ways of representing chemical changes. One way is by using a word equation. You see, this is a word equation here. When hydrogen peroxide decomposes, it produces oxygen and water. All right? So you're going to see the name of the reactant and the name of the product and it change. This arrow here means that it means that things are being produced. So on the left-hand side, these are called the reactants here, and whatever is formed on the right-hand side of the equation are called the products. All right? Another way of representing chemical change is the use of chemical equations. In a chemical equation, the actual formulas for the compounds and symbols for the elements are used. For the previous example, we can have this skeletal equation now. Here is hydrogen peroxide, and it decomposes to give you water and oxygen. This is the unbalanced equation, and it's called a skeleton equation. You can go ahead and balance that equation now. We'll do guidelines on balancing chemical equation later on. Law of conservation of mass. What this law states is that in any chemical change, atoms are simply rearranged and are not created nor destroyed. Thus, the mass of the reactants must therefore be equal to the mass of the products. For example, the reaction that we did earlier, where we mix a solution of sodium hydroxide with copper 2 sulfate, and you ended up with that blue gelatinous precipitate and sodium sulfate. If we have a beaker with sodium hydroxide solution and another one with copper 2 sulfate solution before they reacted, and we place these in a balance, and let us say arbitrarily we say they have 500 grams. And then we pour the solution of one beaker into the other one, and the reaction took place when you form your copper 2 hydroxide precipitate and sodium sulfate. And you took these two beakers again and you weighed them. They will weigh exactly 500 grams. So this is telling us that there's no changes in mass after the reaction has taken place. And this is what is referred to the law of conservation of mass. The mass of the reactants is exactly the same as the mass of the products when they're formed. So we're going to look at this skeleton equation here. Okay? We're using a space filling model of hydrogen peroxide to show you how it decomposes into water and oxygen. Now, what we said before is that there's no change in mass, which means that the number of atoms of the reactants for a particular element must be equal to the number of atoms for that element in the products. So if we check up here, we're going to see if the number of atoms on this side here is equal to the number of atoms over that side. Here you can see that the number of hydrogens here is equal to 2, and the number of hydrogen atoms is 2. So that's fine. But over this side here, we have 2 oxygen atoms, and over here we have 3 oxygen atoms. So the side that has less oxygen atoms must be increased such that when you check the number of all the atoms on that side, it must be equal to all the number of atoms on this side. So let's see how we can do what is called balancing this equation. So we use something called coefficients to balance the equation. Now watch this. Here we see there's less oxygen over this side. So the obvious thing to do is to make more of these, put more of these over this side. So we'll make another molecule of this here, and we get this. When you do that, you're actually doubling the number of hydrogen peroxide. That's why now we're going to put a coefficient of 2 here. Okay? So when you put this coefficient of 2 here, that means you're having 2 moles, we haven't done that, or 2 molecules of these. Now see what happens. Compare this with those over there. We are having now 4 atoms of hydrogen. We only have 2 here. And we are having 4 atoms of oxygen, and we only have 3 here. So the first thing we can do probably is to balance up the hydrogen here. So we have this. So we can actually make another one like that. So you have 4 hydrogen, 4 oxygen here, okay? And whenever you do this, you are doing this now, right? You have to put a 2 here, okay? So this is how we balance the equation. So go back here, and let's see what we did. We had more oxygen over this side than that there. So the obvious thing was to try to put a 2 there. Do not change the formula of anything. You're only using coefficients here. If you put a coefficient of 2 here, it means everything is double. That's why I deliberately show you how you have 2 molecules here. And then now, when you want to increase oxygen now, you put a 2 here now. So that means you're having 2 of these. And we don't trouble that because everything is now balanced. It will not comply with the law of conservation of mass because on the right hand side, you'll have more oxygen than the left hand side. And to comply with that law, we have to make sure we use coefficients to balance the equation so the number of atoms on the left hand side is equal to the number of atoms on the right hand side. So how do you think we can do this one here? Oxygen is fine. Oxygen is fine. But look, nitrogen is not, okay? So what do you think we should do? We can probably make another one of these. Let's check this out now. So what we have this is good. The nitrogen here is good. But we created 4 oxygen. We only have 2 here. What we should do? Put another 2 here. Looks good. You have 4 oxygen, 2 nitrogen, 4 oxygen. What coefficient? Where should we put the coefficient now? We should go now here and put the coefficient of 2. And now you see you put the coefficient of 2 there. And your equation is balanced. I hope that was helpful. So when you put these coefficients, which telling me you double up this one and you double up everything inside here. Guidelines for balancing chemical equations. As noted before, when you balance the equations, we do not change the formulas of the compounds in either the reactants or the products. You use coefficients. How can we go about balancing the skeletal equation here for magnesium oxide? Check it. What do we have? We have more oxygen over this side than over that side. So the obvious thing was to put a 2 here, right? So use a coefficient and put a 2 here, but be careful. When you put a coefficient of 2 here, not only are you doubling the oxygen here, but you're also affecting the magnesium here. So you see, put a 2 here, you're having 2 magnesium and 1 oxygen. When you look at the equation now, this side has less magnesium. By the way, let me get this clear. See this O2 here? It means a molecule of oxygen. You have 2 atoms of oxygen there. Okay? But this is only 1 atom of oxygen here. That's why I put a 2 here. It balances off the oxygen here. Now we have to go and put a 2 in front of the magnesium. You check that out now. You see you have 2 magnesium there, 2 oxygen. So here's some guidelines for balancing chemical equations. So you have different types of chemical equations that you'll have to deal with. So these are general guidelines for balancing the equations. Balance the one element other than hydrogen and oxygen that has the greatest number of atoms either in the reactant or product. So you look at the equation and you see which element is the one that's most numerous. And you start by balancing that one. Leave these 2 guys to the last. Okay? Hydrogen and oxygen. Then, balance the other elements other than hydrogen and oxygen. Balance oxygen or hydrogen, whichever one is present in the combined state, as in a compound, not those in the uncombined state. Let us say you had a reaction in which, say on the product side, you're having H2O and plus O2. You will balance H2O if there is a need for that. Don't Don't balance the oxygen. That's elemental oxygen. It's uncombined. Then lastly, check that the equation is balanced by counting the number of atoms of each element on both sides, okay, to ensure that they are equal. So we go to example now. Watch this reaction here, all right? Watch this reaction here. The atoms of which element is most numerous here in this equation? You can see it's the chlorine here, right? You have 3 chlorines here, and you only have 1 over this side, okay? So what we should do, what coefficient we should use here? You put the 3 here, all right? So next step is you balance chlorine, all right? You put the 3 here, okay? All right. So when you put this 3 here, watch now. Not only does it increase the chlorine to 3, but also the sodium. All right. So now we have to go and put, 1 sodium here, put the 3 in front of the sodium. So you go back now, and you put the 3 in front of the sodium. So this 3 here multiplies the sodium, making it 3. But look, it's also tripling the hydroxide ion here, right? In this case, we have Fe3 hydroxide here. This 3 here means you're having 3 hydroxide ion here. Okay? So this is balanced by itself here. So check the equation. 1 iron, 1 iron. 3 chlorines, 3 chlorines here. 3 sodium here, 3 sodium here. 3 hydroxide here, and 3 hydroxide here because of that subscript there. So this equation is now balanced. Now, there's something I want to talk to you about when you're dealing with radicals. Sometimes you're going to see radicals in an equation. Let's go back to this one here, see? This is a hydroxide radical. When I was doing chemistry, nobody told me that in high school. I should break this up into hydrogen and oxygen and everything. Nobody told me, hey, don't break this guy up. It goes as a block. It goes as a whole. You don't trouble these radicals like nitrate radicals, sulfate radicals, carbonate radicals. Don't break them up. You just take them as a group. Why that is so? This is a nitrate radical here, okay? When you look at this nitrate radical here, effectively what is happening is that you're having 3 oxygen atoms bonded to the nitrogen there. So they're all grouped together. And that is why now they'll move as a group. So we can see like we have a box, right? And this box, we label it nitrate. So you move this guy, it goes as a whole. You're not moving the nitrogen away from the oxygen, right? For example, in this formula here, iron 2 nitrate, what do we have? How can we separate this? You have 2 nitrate ions. See that? 2 of these because of this substrate here. Okay, and you have 1 Fe. So that is like equal to 1 Fe2 plus, and you have 2 of these here. If I put a coefficient of 2 in front of it, what does it do? It multiplies this guy by 2, all right? But now, how many nitrates will you have? This 1 here give me 2. So when you put a coefficient inside here, everything gets doubled. So I'm going to have 4 nitrates, okay? So this will be equal to 2 of these and 4 of those. Let's see how the reaction here. We're reacting these guys and get FeOH3. What does that mean? Means you're having 3 radicals here of OH. And if you're to count the number of atoms here, you'll have to do this later on. It'll be equal to, that's not right. It'll be equal to 3 of that, 3 oxygen, and 3 hydrogen atoms. Okay? So let's do another one. So this is a reaction we have to balance. What are you looking at? Look at chlorine here. You have 2 chlorine here, but only 1 chlorine here. The obvious thing now is to go and put the 2 here. So you put a coefficient of 2. If that was 3, then you put a coefficient of 3 here, okay? So you put a 2 here. When you put this 2 here, it also doubles the silver. So, but now on this side, you only have 1 silver. So now you have to go and put the 2 there. So you go and you put the 2 here, okay? So this 2 doubles the silver and it doubles the nitrate. But check on this side, look. Because it's calcium nitrate, you have a 2 there, okay? A subscript of 2 means you have 2 nitrates. Check it out now. So you have 2 silver, 2 nitrates, 1 calcium, 2 chlorines, So now you have to do your work now. You'll have to go now and balance all these equations that are given you here to do. All these here, solutions of these, are found in your solution manual. And I hope that was helpful to you.